Where? So I get this. Oh, there one. Never mind. From current slide. Yeah. Okay, guys. Hope everybody can see the slide. I'm going to turn my. What we didn't do yesterday, and I must apologize, is that just to sort of sort out where everything is coming from. I'm from, and myself and Songo from Green Building Design Group, the Green BDG. We're just facilitators of this session, and it is actually this Building Efficiency Accelerator program that ICLEI is doing. So you can see with underneath all the names and all the people involved in this program. So just to let you know that we are just facilitators. So if we talk about the BEA, then we're talking about Building Efficiency Accelerator. So I just wanted to be clear, so we've added that slide into the presentations. Okay, so I hope you're all ears and you're ready for the next piece of the puzzle. So just go back a little bit. I think you remembered this, is that basically for performance of the building sections, we look at the concept of thermal resistance. We look at the R value of the different makeup of the building. And the R value is thickness in meters divided by thermal conductivity. Thermal conductivity is measured in a laboratory. Again, where do you get this number from? You have to get it from the manufacturer. It's a tested product, tested property, and they must give it to you. So there's no guessing about it. They have to give it to you. Okay, and as I said, yes, Kieran. Do you want to chat, ask a question? Just put your microphone on. Okay, I can't hear you. Maybe send something with WhatsApp, I think. It's chat box. Oops. Oh, wait, let's just see. The chat, let me see. Yeah, can't see. Okay. Please, we've got a question. I can't hear anybody. Yeah. 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 So yeah, I think put it into the chat box, and we will address it in the afternoon session. Because at the moment I can't answer in the middle of everything, and I think it's good for us to share questions so that everybody learns from them. Okay, so let's start with how we build buildings, and we start with the flooring. Okay. So currently in 10400XA, what it says for flooring is only that if you have underfloor heating, then you have to have an insulation underneath it with an R value of 1. It says any panels to interaction. Okay. Okay, let me add you as panelists, and then I think then you can interact. Because Kieran, I see what your question is can a manufacturer lie about the values? And they can, but the thing is you then need to show that you can ask them for an SABS test. Okay, bear with me, I'm going to promote you to panelists. And you'll be able to interact. So just bear with me, please. Promoting everybody to panelists.
All right, can you hear me now?
Yes, I can hear you. Great. Kieran, please ask your question.
Yeah, well, see, with the world we're living in now, and there's so much of corruption in every sector of society, obviously now with all this environmental impact and the need for thermal efficiency in buildings and stuff like that, right, which is now becoming law in South Africa. I lived and worked in UK for a good 5 years, and this was 10 years or odd ago when they first started. They were already ahead with this U value calculation and stuff like that because of thermal bridging and stuff like that, right? What had happened, what we noticed there was there are a lot of products that were on the market that all claimed to be doing, what they say it does on the tin. But eventually, what started happening was people started finding that there were flaws and hidden flaws and purposely hidden flaws in terms of the data that the manufacturers were giving, simply because of competition. So, is it possible that manufacturers can lie to basically so-called up the quality of the product? I think it would be possible for them to lie and get away with it for a long time before somebody realizes, because at that time when they were trialing all of this in the UK, what was happening was a lot of guys had already given a projected U value or R value or something, but the product was still being developed. So a lot of people were installing things thinking that that's the desired, they will achieve the desired outcome. But what was happening was when they did the install, they found that the product wasn't really doing what it's supposed to be doing.
Yeah. Kieran, can I ask you, I'm going to go into insulation products.
Yeah.
Let me get them, cover it, and I'll answer your question then. And if I don't quite answer it, then just ask me again, okay? But I do cover now insulation products and their values. So, because you're right, you're totally right.
As an aside, I'm gonna tell everybody a small personal story. We've been having issues at home with regard to heat in the ceiling space.
Yeah.
Right. Well, I went out and I bought isotherm insulation, the 100 mil one, which is supposed to give you the most optimum temperature inside the house. So basically, what it says is it keeps your house cool in the summer and keeps it warm in the winter, that kind of thing.
Yeah.
And I tell you what, I've done probably 80 odd or 100 odd squares of ceiling space with it. It made no difference. Absolutely no difference.
Yeah, because it's not sufficient. 100 mils is not sufficient, and that's why
they tell you we had the option of 50. So I opted to go 100 because I know how hot it gets in the ceiling, and it was just madness. It made absolutely no difference. So how much? And it's not cheap too.
Yeah. No, and that's the problem with it, and that's, as I'm saying, let me get to where in for your area, what you should be looking at, and what does it mean in terms of what thicknesses of different materials you're looking at. And because I agree with you totally, and I will tell you some horror stories as well. I mean, and it's also, let me tell you the funniest story ever is that I used to work for Sanger-Band back in the day, and the product we had was Think Pink Aerolite. And I had a phone call from a homeowner, and she said to me, "Look, your stuff just doesn't work. There's nothing happening, and it's my house is as cold as ever." So I went to the house, had got the ladder, put my head through the trap door, and around the trap door was perfectly installed aerolite. And what it is, I went a few steps up, and in the ceiling were the rolls of unrolled product that was just left inside the ceiling void. So, when you talk about people not quite playing open cards with their clients, these are typical examples. And so I said to the homeowner, have you checked in your ceiling? And they were like, yes, we checked. And they hadn't checked far enough. And obviously they called the person, and they didn't, got the money back, and got a reputable person to to install. But yeah, the values and the R values are very, very important. And as I say, let's get to the installation side, and I'll let's expand on it and how you can check it and what you can look for on, because people do, let's not say lie, let's say mislead the people. Okay, so I'll get to the installation. Okay, let's get back to flooring. Please, ask questions as we go. So if you look at, as I said, the current 10400XA says the only time you have to insulate flooring is for underfloor heating. And then you have to have an insulation with R value of 1. As I say, we'll go into how to check R values and see what's what. Okay. But now the new version of 10400XA has, oh, Jabu, I think we can hear you. Don't you just put your self on mute? Thank you. So what the new version of 10400XA says that if there's suspended or exposed flooring in some regions, then you have to insulate it. Now, what is suspended or exposed flooring? If you think of a building with a parking area underneath it, that the roof of the parking area is the floor of the building. And so if you think of it, we said, okay, we'll get the walls to a certain performance, we'll get the roof to a certain performance, but we've got this huge gap underneath that is now a heat sink. So everything's going underneath it. So the committee decided that in energy zones 1 and 2, there'll be insulation of R value 1.5. In 3, 4, 6, and 7, there's insulation of R value 1, just to complete the envelope. Except in your region. Because what, as I said to you yesterday, is one of the things we don't want to do is to form a hot box. We want to stop the heat getting into the houses, but we don't want to trap heat in the houses. So if you think of how they build in areas, these like the Philippines or Thailand, and they put the houses on stilts. One of the reasons for putting the houses up is that then the prevailing winds from the ocean then blow underneath the floor, and they actually form a natural coolant. And in buildings especially with high humidity areas, if you have an exposed floor and there's a sort of ventilation underneath it, it actually acts as a natural coolant. So the one thing we don't want to do in the hotter zones is make these hot boxes, and we want to facilitate cooling because there's it's not huge. It's unexposed flooring is not going to cause too much heat gain. It's the benefit of it being open is much better for those areas. So in your area, with the new version of 10400XA, you don't have to worry about exposed flooring because it doesn't ask for it to be insulated. So let's look at walling. Let's just go back again. Now, just if you look at flooring, okay, I spoke about the insulation R value 1, insulation R value 1.5, and insulation R value 1. When we talk about flooring and when we talk about the roof and ceiling assembly, we talk about the system R value. So we look at the performance of the whole system. So in flooring, you're just looking at the value of the insulation. But when you look at walling and you look at ceilings, then you look at the R value of the total system, because again, they're made up of different materials. And we could ask the question now: why don't we just say to people, just use this product because that'll comply? Is we don't want little boxes. We don't want copies of buildings. we want the professionals to be able to design as they want to a point, but as they want energy efficiently. We don't want to rule out any materials. We want innovation. We talk about innovative building technology, IBT. We talk about alternative building technology, ABT. And if you're prescriptive about the material that's used, what happens is that you don't get this innovation happen. But you don't want innovation to happen, which then doesn't comply with the performance of the system. So we want to say, look, you can bring whatever you want on board, but the performance of the wall has to be XYZ. The performance of the ceiling and the roof assembly has to be XYZ. So let's look at walling. So in walling, we look at the R value total, or the R value of the system, and it's basically looking at 1 + 2 + 3 gives you the value of the system. When we started writing the 10400 XA, and Kieran mentioned U values. In the UK, in a lot of places in Europe, they use U values, which is thermal conductance. It's sort of similar to what we talked about for windows. But when we started, we looked, and Australia uses R values, and we work quite close with them. And the reason why they used R values is because they're additive, they're easier to understand. And you know that you can do 1 + 1 plus the next one, and you can get the total value of the system. So we just felt that it was sort of more user-friendly and easier to understand than U values. U values are slightly more complicated, but not non-understandable. But it's just we felt for our market that R values made more sense. Okay, so for walling, we have divided walling up into masonry and non-masonry walls, or densities. So examples of non-masonry walls is timber frame buildings, steel frame buildings. So buildings that don't have concrete or brick, basically. So it's the lightweight construction. So for lightweight construction, we say that for climatic zones 1, 2, 6, and 7, you must have an R value of the system must be 2.2. And for climatic zones 3, 4, 5, and 5H, which is your area, it must be 1.9. And as I spoke about, flooring, insulation R value, walling, system R value. The difference is that one, you ask the manufacturer, what's the insulation R value? The system, you must know the R value of, so say we're looking at a lightweight construction. So let's look at a typical steel frame construction. Inside the interior wall of the steel frame construction will probably be a plasterboard. Then there'll be insulation, perhaps a vapor barrier, generally a vapor barrier, and then an external cladding, so like an everite board. So the R value of the system would be the R value of the plasterboard plus the R value of the insulation. The vapor barrier doesn't really have any R value, it's just thin, it's there for water. And then, so it's R value of the plasterboard plus R value of the insulation plus R value of the external everite board. And that must add up to 1.9 in your area. So, and that must come from the designers, and it must be on the plans that the walls comply with this. If it's lightweight, it must comply with this. So when you're looking at masonry walling, you look at something a bit different. So this picture has shifted. I'll try and move it for the when I send you the copies, I'll shift it. So masonry walling is basically walls greater than 270 kilos per square meter density. And currently, in the current 10400 XA, it calls for walls of R value 0.35. And in the new 10400 XA, it goes one further and it calls in some energy zones, including yours, it's still 0.35, and in other energy zones, the R value is required is 0.5. Now, what are those numbers? What it says in the standard is that if you build a double brick wall, you will get an R value of 0.35. So it will be deemed to satisfy. So you don't have to ask and it has to be plastered internally. You don't have to ask the manufacturer what's the R value of the brick, because in the standard it says if you build double brick wall, you will get an R value of 0.35. Now the R value of 0.5 is actually a cavity wall. And what it says as well is that if you build a cavity wall, you will be deemed to satisfy the 0.5. But now, if we're giving you deemed to satisfy, why are we now still putting an R value of the system up? And one of the reasons is, as I told you, is if suddenly we get an innovative building technology, say we build our walls out of a different material, then we would need to know what the R value of that material is. And we would need to know that when they've built this wall, it matches this R value of 0.35 or 0.5. So it's very important that we understand that the performance of it. The other thing is, I don't know if you're aware, but in the interior of the country, we don't really build with cavity walls. It's always been double brick. The only areas that we find that people build cavity walls is along the Cape Coast. And so there's a certain expertise, there's a certain skill set that people can build cavity walls. So I'm sure you know that cavity walls are not that easy to build, or clean cavity walls. There's nothing inside them. People sort of don't understand that the idea of the cavity walls, the insulation value comes from the space in the cavity, and that if you throw a bit of brick and dagger inside that cavity, you're not getting the R value that you need, because you're making a solid brick wall again, basically. You're getting this thermal bridging, and you're making a solid brick wall. So this cavity has to be clean. There's obviously the it's still calculated with the just think of the, I can't think of the word now, but the bars that hold it together. I'll think of the word now. And so that is where we don't have the skill set in the interior of the country. So we're saying, okay, if you cannot build a cavity wall, a good cavity wall, you can still build a double brick wall. And if you look at the picture on your right, there's a cavity wall, and the one just below the cavity wall, you'll see it's got like an insulation and a screed on it. It's a polystyrene insulation and a screed on it. You can still get the R value of 0.5, the single brick wall plus insulation on the outside with a screed. The other one shows you an internal lining that you can do with insulation and plasterboard. So what we're saying is, if you can't build a cavity wall, there are means of still getting to that R value by building up double brick plus insulation. So again, we want to give people choices of how to build, but we want the performance. Now, as I didn't really say in the beginning, is that no country in the world has written their energy efficiency standards and said, oh, there are we done. We've got such a great standard, we never have to look at it again. Bearing in mind that 10400XA is a minimum standard. And in our chat yesterday afternoon, I said to you, these standards can't be seen to be inflationary. They can't add to the cost of things without having some payback. So when we did the first 10400XA, the National Building Regulation falls under the Department of Trade and Industry. The DTI said to us, okay, let's have an introductory 10400XA. We are not going to go all hogs. So, I spoke about SANS 204 that was written pre-10400XA, and they felt that the stuff in SANS 204 was too high. It was at too high a level that would shock the market. So the 10400XA that we wrote was the introductory, like almost introduction to energy efficient buildings. But what the DTI said to us is that every 5 years, we must then rewrite the 10400XA and up the performance levels that we need. So now we're a bit behind the times. It's more than 5 years since the first 10400XA was published. But one of the big things we had to change was the map. People said the map wasn't accurate. So the CSIR took 2 years to get the map right. So we were really, really delayed. So if we've now done version 2, as I said, it's been out for public comment. It's probably going to go out for public comment again. Once it's published, they've asked us to then start the next version of 10400XA almost immediately, because we have to get up the level again. Now, why am I telling this whole long story? There's a reason. Because from version 1 to version 2, if you look at the differences, we didn't change the lightweight construction requirements because we found them to be sufficient, but the masonry walling requirements had to go up a bit for a better performance of wall. So this is our step-by-step way of getting to a better performing building, is that every time we do a version of 10400XA, it will slightly increase the requirements, and we will get, finally we'll get to like the optimum buildings. So you'll see at the bottom left-hand side, there's this a cavity wall with insulation in. That was the first proposal we had, but they said again, it was a step too far. So probably in version 3, we might be looking at a cavity wall with insulation. So just a bit of backgrounds and on where we came from and why there's this version 2 and why I'm giving you guys heads up about this is what's coming, so that you are ahead of the game. And again, you don't have people submitting plans to you telling you what is the truth. You will know the truth. Okay, and the one other thing about walling is we talk about the exterior walls. What is an exterior? An exterior doesn't necessarily have to be the outside of the building. And if you look at these drawings, if you look at 10400XA, it excludes garages and storage areas. So now, and I always say to people, if you love your car very, very much, you can make your garage energy efficient. It's up to you. But the rules, the 10400XA doesn't ask for garages to be made energy efficient. As long as the inefficient garage does not impact on the efficiency of the main building. So if you look at those drawings, is that what happens is that if you exclude your veranda, your solarium, or your garage out of your from your energy efficiency, then your external wall, or your exterior wall, becomes the one between the dwelling and the garage and veranda. Now, we've been asked again what, people say, oh, I converted my veranda into whatever. What does it mean? Well, again, if you convert your veranda into a bedroom, then your veranda has to be energy efficient because it's part of a dwelling. It's an occupied space. It's part of the house. And then your external wall and your windows and all that has to be compliant to 10400XA. If you enclose your veranda, you just put down a, those blind things or the stuff that stops the wind, because you want to now make your veranda into a place where you can braai, then obviously it doesn't have to be energy efficient because it's not a living area, it's not a living space. And then the question you ask when you look at it is, does this not, so does if we don't make the veranda, solaria, or garage energy efficient, how does it impact the main building? And the answer must be the main building's external wall is then the wall between the garage and the solarium. So, and I've come across in some municipalities and some PTOs, they've said that if a shopping centre or a building has a solarium, they've just excluded it out of consideration for energy efficiency and for the 10400. But they've never asked themselves the question that did that solarium impact the main building? Because they've said they haven't necessarily seen a wall between the solarium and the main building. And obviously, if you've got a huge solarium, say in the bottom floor of an office building, of course it impacts the energy efficiency of that system, because there's going to be so much heat coming in there. It's going to have to be cooled to the nth degree. So it's really, when you look at buildings, look at the impact of these things and understand that then you just say, I'm shifting the exterior wall to this, and the exterior wall must have the right performance. Okay, we spoke about cavity walls, and as you can see, we've got bad cavity walls. I don't know if I'm going to be able to link. I've got a video of the cavity wall. I don't mess everything up.
I don't know what.
Lisa,
Yes.
sorry, we can't hear or see the video.
Can't you?
No, we're still seeing the page that you had put up with the bad cavity walls.
Okay,
we
let me try. And I think I must just go back to okay, sorry, we're going to do it again. I just assumed you could see my screen, but I think it's Or maybe I can just make it smaller. Can't we just press on that to share screen? If we make, if we just make this smaller, let's get rid of that. That's amazing, Shay. Okay, guys, can you see a new screen?
Yes, we can now.
Yes.
Okay, perfect. Thank you, guys. Again, BBC here, but hey, you're teaching me as I go along here. Yeah. Yeah, yeah, we start. Hey, can you hear?
No, we can't hear. We can just see the visual.
I can hear.
Can you hear it?
Can you see the video?
I can hear it. Yeah, I see the video.
Can you? Okay, can you? I'll play. If you can't hear, I'll take the sound off and then just explain it. But basically, what you're looking at is, let me sort of put some background context to it. Is if you look at the difference between lightweight construction walls and sort of masonry type walls, the difference in the thermal performance is something that's called thermal capacity. So over time, brick or concrete absorbs the heat of the sun and slowly releases it. And when the outside gets cooler, again it retains some of the heat and then slowly releases it. So this video demonstrates how it works, and you'll see by the temperatures, and you'll see the sun going up. So even if you can't hear, it's very visual. You'll understand what it's about. So let me play it, and then we can discuss it when it's done. Okay.
Sorry, getting feedback from Q.
Let me just stop that. And okay, how do I get out? How do I get back here? Sorry, Sandra. I'm now like, oh, it's just here, hey? Yeah. Guys, can you see the screen again?
Yes.
Yeah.
Okay, so we're back at the presentation.
Okay.
Great. Okay, so again, as I said, the video was just because people always ask me, how do cavity walls work? What is the, you know, why have a cavity wall? And that's just really what we're looking at. So, and as I said, the difference between lightweight construction is lightweight construction depends totally on the R value to give energy performance, whereas the masonry walling or the heavyweight construction has a combination of the wall has thermal capacity plus some insulation. So that's what we look at. And as I say, when we look at cavity walls, we don't want cavity walls filled with anything, because then they are no longer cavity walls, they are solid brick walls, solid walls. So this is just some examples of stuff we've seen on site, of just how badly, oh, and the word I was looking for was wall ties. Something came in my head. There are wall ties inside the cavity wall, but the performance, the R value of that includes everything, includes the construction of the cavity wall. Okay, so let's go on. Now, you know, we had a long chat yesterday about affordable housing, and I said to you that even in their norms and standards, they had increased the level of energy efficiency inside the government subsidized houses, and they had increased the budget to cover those increased requirements for materials. Cool. Kieran, I think you're giving us feedback.
No, I'm actually trying to find how to raise my hand.
Okay, sorry.
The first time I'm using this thing, so bear with me.
Hey, you and us all, hey?
Yeah, quick question, right?
Yes.
You say that obviously cavity walls should not be filled with anything. Coming back from my experience in the UK, some, especially in high-rise buildings, flats, you know, multi-story residential apartments, what they used to do there was they used to fill the cavity with expansion foam as well, because it also acts as a fire retardant, and you know, fires and gas use and stuff like that in UK is very common.
Yes.
So the expansion foam that they used to use was a fire retardant as well as a heat retardant. So that way it helps to keep the inner
Yes.
house, you know, at the regulated temperature. And you know, they don't use full masonry construction like how we do here. The inner skin is usually brick. Sorry, the outer skin is usually brick, or fake brick, or whatever it is. And the inner skin is a drywall partition.
Yeah, because that's just go back a bit. So yeah, so again, when I say you mustn't fill a cavity wall with anything, you obviously can fill it with insulation, because that has an insulating property and it's got an R value. So it's got a thermal resistance. It prevents the ingress of heat or the outgress of heat. So Kieran, you're right, and that's why we say that we still give a performance value for walls, because you know the constructions you're talking about, and they're common in the UK, Germany, France, is they use sort of these combinations of wooden construction to come up with, and when you add them together, they have the right performance. So when I say don't fill a cavity, okay, you can fill a cavity with insulation. What I'm saying is don't fill a cavity with brick or dagger, or, you know, I've seen places where people use it as some kind of storage unit. So it's very, very strange. And we're saying, you know, it doesn't have the right effect if it's filled with a solid, non-insulating material. So yeah, so you can look at, and that's why I showed you these different walling constructions, is that you can look at different combinations of materials with insulating properties that can make up a really good performing wall. So you're right. Okay. But it's just, yeah, we don't want stones and bricks to be filling it. Now, let's go back to government subsidized houses. So what they did in 2013, and it was made mandatory for them from April 2014, was that for government subsidized houses, they included that you had to have plaster in the interior and exterior. Now, again, as I said to you, why did we start with this whole plaster story with affordable housing? And in the South Cape condensation area, it was because of mold growing on the wall. Because again, if this wall is not well sealed, you get moisture ingress, and the moisture ingress and then it goes inside. The walls are damp, it's nice and warm inside, and the mold grows like a demon. When the spores open, it causes problems, especially with children, and especially with children with asthma. So it really causes respiratory problems. So if you look at this, and somebody mentioned yesterday that it's not even a plaster that they use in the affordable housing sector, it's this bag wash. Now, bag wash does not cut it. Because if you understand the reason for the plaster is that you want to prevent moisture ingress, and you also want to prevent that there's a surface for the mold to etch onto. If you understand that, you understand that bag wash is not equivalent to plaster. Because does bag wash prevent the moisture ingress? No. Will the bag wash prevent the mold growth? No. And it's a health issue. So if you look at mold, it's a huge health problem. And as I say, especially for children. And so when somebody comes and says, oh no, I have complied with your requirements because I put this bag wash on, really your answer should be, no, you haven't. And if they ask why, and we spoke about you're hindering my progress. So, well, you're hindering people's health. So it's really important that, and as I say, the budget covers this. The budget includes plaster inside and outside of walls. Okay, so let's look at the next part of it, which is the roof and the ceiling assembly part. So in the current SANS 10400XA, in those different climatic zones, you'll see that we've got a range of R values for the system. And it ranges from 2.7, 3.2, 3.5, and 3.7. Okay, and I'll talk to you now about this up and down direction of heat flow. In the new 100XA, in version 2, it's about to be published, well, probably towards the end of the year. What we've done is we made it simple. We've said, look, the difference between 3.2 and 3.5 and 3.7 is not that great. Let's make it simpler. So what we've done is we've taken the country and we said, okay, in the high humidity zones, we need an R value in the ceiling of 2.7, which is not a change from the current 10400XA, but in the rest of the country, we want an R value of 3.7. So, and again, it's with this view of not making this hot box. Now, this direction of heat flow, it's when we looked at the heating and cooling energy that's needed to make buildings thermally comfortable for people, we said, okay, when the map was done, when we did all the calculations, we said, what is the driving or the dominant energy requirements? So if you look in zone 1, which is the sort of bigger interior zone of the country, so take a place like Bloemfontein, Mangaung. you have really hot summers and really cold winters. And we said, okay, what is the cooling energy needed in that area? It was, say, X. And what is the heating energy needed in winter in that area? And we found that it was X plus Y. So the dominant need for energy efficiency in zone 1 is the winter heating that's needed. So if you look at it, you heat inside your building and the heat goes up. Because it's not like, I don't know if anybody, the ladies or anybody's wives have got what we call a summer and winter cupboard, you know, a lot of clothing, I think, and I don't think so much in your area, but here there's like, you got a winter cupboard, you got your winter clothes and you got your summer clothes, and people change it. You can't do that with your roofing insulation. You can't like say, oh, here comes the summer, now we change the value of the insulation that we've got. We had to put in the right amount of energy efficiency for the dominant use of energy, the greater use of energy. So if you look at zone 1, 2, and 4, and 6, you'll see that the main need or the main use of the biggest use of energy is for heating energy. So it's the heat inside the building going up. If you look at zones 3 and 5 and 5H, which is your zone, the biggest energy requirement is cooling energy. So what we want to do is we want to stop the heat from the sun coming in and the heat flow going down into the building. And that's what this up and down thing is. So just that you, and it's there really for the technical guys, the guys that do the software calculations, but just that you know what that means. So, so this is how we simplified it. So when we looked at, as I said, we decided we're going to up the levels of 10400XA. What we decided is, because we had set levels for the roof and ceiling, we'll just simplify them, and then there's one more thing that we did, where I'll go into now, but we didn't change the numbers. Okay. So let's look at how to calculate the R value of a roof assembly, and as I said, it's the same with the wall. So we've got this typical roof. We've taken the direction of the heat flows up, so it's a 3.7 type area. Now, what you have when you look at your requirements for R value, there's these little things called outdoor air film and indoor air film. Think of when you stand next to a wall, you will either feel that right next to that wall, there's like a slightly cooler feel or a slightly warmer feel, depending on if you're inside or outside. And that little film of air adds to the R value of the system. So we do include it. But when you look at 10400XA, you'll see it's a typical roof construction, and it'll say what the roof construction is and what the intervention of the insulation, the R value of the insulations that needed. So understand that inside the 10400XA, there these indoor and outdoor air films are included. Okay, but be that as it may. So you take the roofing material. There's an air space in the your ceiling void. You've got the insulation. You've got your ceiling board, and you say, okay, what do we have? So each of these has a value. Roofing materials 0.02, the airspace 0.18, the ceiling boards 0.06, and so you add that all together and you say, okay, what insulation requirement, what R value of insulation will give me my required value of 3.7? So basically all those things add up to 0.4, so you need a 3.3 intervention, and in this area it's equivalent to 135 mils of glass wool. Okay, but now the thing is that well, we'll go into the insulation, but let me just go back. If you look at it, we said we want an intervention R value of 3.5. So before we talk about the thickness of insulation, we have to understand what the R value is required. And I'll touch on this and I'll expand on it now, and it should answer Kieran's question. But now the other thing is that, and I don't know if you've seen it in your area, is there's this concept of cool roofs or cool surfaces. And there's also radiant barriers, which is like a sisylation or an alu bubble, alu cushion type thing. Now, obviously, these insulations don't have thickness. So you can't get it to a real, you can't say, okay, thermal conductivity of a sisylation is this, and its thickness divided by the thermal conductivity. They don't work like that. They work in what we call, because they have high reflectance and low emissivity. So basically, as the heat hits the cool surface, it will only emit part of that heat down into the building. So the radiant barriers, the cool surfaces, work well in hot areas. And what we do is we give them an effective R value. So we say we can't measure the R value, but there's an effective R value. So inside SANS 10400, you will see the effective R value for radiant barriers, or for, and let's be the sisylations and alu bubbles and that kind of thing. And it's based on what the emissivity is. So normally I use lots of hand gestures, whatever, but if, as I said to you, it's the heat from the sun comes down, reflectance plus emittance equals 1. So the more the product reflects, the lower the emittance down into the building. So it basically just prevents that emittance going down. It's not really, it doesn't work well in upward flow temperatures. So it doesn't work well for winter areas, but it does work well for hot summer areas. And the other thing, as I said, we did not say, you know, let's not up the level for the new version of 10400 XA, but what we did say is that let's minimize thermal bridging and compression, and I'll show you how we did that, and I'll also show you when you'll see it, you'll see how to look at thickness and performance of insulation products. And I've said the minimum R value is deemed to include the thermal bridging by the framing members. So often we get people that are like, they say, oh, you measure the R value of a material or thermal conductivity of material in a lab. Now when, think of, Kieran, you were saying you put isotherm into your ceiling, you put it between your beams, your sort of bridging, your framing members. The R value, the effective R value has been, we've included that thermal bridging that will come from the beams and the rafters. So you don't have to like do a whole recalculation, because we said if you have an insulation of R value, say 3.25, it normally is, and you put it in between your trusses, we will say that yes, that total roofing system achieves the R value that you want. So you don't have to do a huge calculation and take into account thermal bridging and things like that. And as I said, what we decided is, instead of changing the R value of the sealing systems, we said let's just make sure that the insulation systems that you put in buildings works better. And I don't know if you've seen metal buildings, they normally have a blanket insulation, and they will, it compresses at the purlins, and then you've got straining wires that hold it on. Each of these things, at the purlins, at the straining wires, it shrinks the actual thickness of the insulation. Now, bearing in mind, R value is thickness divided by thermal conductivity. The if you make it thinner, the R value is less. And so what we said is, okay, let's not increase the R value, but let's make the effectiveness of the insulation better by putting in systems that don't compress it. So in the new version of 10400XA, you'll see that for metal buildings, it asks for a spacer system for compressible blanket insulation. Okay, so let's talk about insulation. And this is what we were mentioning. So let me go to your area. Okay, 5H. If you look at it, we need the typical insulation value back in this area is 3.25. So 3.7 minus all the other roof construction. So the insulation value that's generally needed is 3.25. And in your area, it's 2.7. So the insulation value is normally 2.25. Now, if you look at it, we've got cellulose fiber, we've got fiberglass blanket, we've got polyester with 11.5 density. That's generally where the isotherm falls into. We've got higher density polyester, 24. We've got expanded polystyrene. We've got extruded polystyrene. We've got fiberglass board. We've got fiberglass blanket, and we've got the foams. Now look at each of those has a different thermal conductivity, the K value. K value is the thermal conductivity. So it ranges from the cellulose fiber and the fiberglass blanket having a thermal conductivity of 0.04 to the polyester blanket as having a thermal conductivity of 0.046. Now remember, thermal conductivity, the lower the thermal conductivity, the better the insulation. But now, so let's take, we want an R value of 2.25. What is the thickness of material needed to achieve that R value at those thermal conductivities? And if you look at the isotherm, you need to be looking at least 110. And in your area. So if you look, and it's even more pronounced if you look in the 3.7 area, is that cellulose fiber and fiberglass blanket you need 135, but a polyester blanket you need 155 moles. The other thing you'll notice is with the extruded polystyrene, I've added a note of, and with polyurethane and the polyisocyanurate, there's a note of no sealing. Now, why have I said no sealing? I don't know if you've come across extruded polystyrene. It's an isoboard type of sealing. They don't have a sealing board. So the actual board, the XPS, is a tongue and groove sealing system. So now, if you take out the plasterboard sealing, you're taking out an R value of 0.06. If you take anything out of that system, you have to add that R value back into your system R value. So even though if the extruded polystyrene, if the isoboard was sitting on top of a ceiling, the thickness required would be less. But because it forms a ceiling, you have to add that R value that's missing from the ceiling into the system. And then it comes to that for extruded polystyrene, you need a thickness of 70 moles. Now, I don't know if any of you, I haven't seen a tongue and groove polystyrene system that's 70 moles. And it's one of the things. Yes, Kieran?
No, well, I'm just looking at this, the values that you're talking about here, right? Where we're looking at polyester, or the green polyester fiber blanket.
Yes.
And as you said, it's 110 mil the thickness, right? That effectively would be enough thermal insulation to be able to combat the effects of heat loss and heat gain in the building.
Yes.
This is the stuff that I actually do have at home, and it's not working.
But you said you've got you said you got 100 moles though. So you muted again. But yeah, you've got 100, and I mean, you think that the 10 moles does make a difference, but it does. Yeah.
Okay.
No, it doesn't sound like a lot, but it is. Trust me.
10 moles
Because
on a
again,
wool blanket.
yep, it makes a difference.
Well, would it not be 110 on the packaging maybe? And I'm just assuming there's 100. Okay, let's just even say it's 110 moles, right? But it's making
Yeah.
no difference to be honest with you. It's not.
Yeah.
You know. It's
Okay,
not.
it should, but look, maybe you need. Yeah, it depends again on your
You know, I want to
construction
tell you
of your
something.
house.
Yeah,
Do you
I
have
want to tell
lots
you
of
something.
windows?
No, there's just one window in each bedroom, one in each bathroom, and two in the kitchen.
Okay.
But the ceiling void is quite big because it's a 22.5-degree pitch
Okay.
roof, tile roof.
Yeah.
Having said that, though, metal roofs will attract
Yeah.
more heat, obviously, right?
Yes. Yes.
I have a little storeroom down in the garage which has a metal roof on it, and believe it or not, I was looking at the time. Money wasn't the grandest available commodity, so our neighbors bought a whole lot of appliances, and it had in the fridge boxes and stuff like that, a whole lot of flat polystyrene sheeting.
Yeah.
So I actually used that flat polystyrene sheeting. There must be about like 15 or 20 mils thick, and I stuck that in between the underside of the metal sheeting in the garage, and I put in a raked ceiling, plasterboard ceiling. I'll tell you what, it is permanently cool in that space. No matter how hot it gets outside, it's permanently cool. So I think polystyrene is a better insulation than this rock wool fiber thing.
Yeah. Look, it's again, you'd have to look at the construction. I mean, as you say, you've got a high ceiling void, and again, I would also look at. They must give you and I'm sure you haven't got the packaging anymore, but let's look at the density of the stuff, because there's some polyesters out there. I must just tell you now, I've seen them where as you hold them up to the light, you can actually just see right through the blanket. And if you can see the light, that means the air is just flowing through it. It has to be quite dense. And it could be to do with the density of the material. So if you look, and that's why I put densities there as well, because obviously the denser material have different thermal conductivity values, and and maybe you'd have to go to a thicker value. And you see and the difference between the boards, so the polystyrenes and so the polyurethanes and polyisocyanurates, is that let me go back. The polyesters, the cellulose loose fill, and the glass blankets, which is like a Think Big Aerolite, they work because the fibers trap air. So that, and it must be still air, because if the air moves, obviously it's like think of a flask that you hold your coffee in. You've got your material, and then you've got like a vacuum between the outer wall of the flask and the inner wall of the flask where the coffee is contained. That's something similar, but you see, so what you've got there is you've got what we call like still air, and that sort of stops the heat going. Well, it doesn't stop the heat going out, it just slows it down a lot. So what the sort of blanket type insulations do is the fibers must be sort of thin enough to hold these little pockets of air and not allow these pockets of air to move. And so when you hold up an insulation blanket, you should not be able to see light through it. You should not be able to see through it, because it has to be able to be thick enough and dense enough to hold those little pockets of air that prevent that just slow down the movement of heat. What happens with the boards, the polystyrenes and polyurethanes and isocyanurates, they've got what they call blowing agents. So so they come, a polystyrene is taken, they come in little polystyrene beads. They're normally filled with a pentane. And as you sort of add heat, they blow up into this board. And so they don't trap air, they trap these other things. They trap pentane or different chemicals, and these, what we call blowing agents, they've got a very, very low thermal conductivity, which means they've got a good thermal resistance. And that's how you'll see thickness with thickness. The boards are probably more effective at a lower thickness because they've got the sort of, it's not air, it's a chemical that they've trapped. And it's not a dangerous chemical, so don't stress about it. Well, some of them. Polystyrene is very inert, and that gives its thermal properties, is that trapped blowing agent. And that's why the only thing with the boards, the foam products, is that obviously they are combustible. So you have to see where you put them and where you apply them. So the polystyrenes, the extruded ones and the expanded ones, are combustible, but they're not toxic when they burn. They've got less toxicity than wood. But the things like the polyurethane and the polyisocyanurate, they are based, when they burn, they release what we call cyanuric acid, which is very toxic. So, and it's not saying, again, it's not saying don't use them. It's horses for courses. You use it in an area where it's not going to be, that people can still escape in the case of a fire. So, and in housing, you can use polystyrene and the combustible materials, because again, the view is that there's only so many people living in the house, and you can escape and safely and quickly. So sorry, I'm going a bit into a bit of a tangent. But what I would say to you is really look, if you can, I know it's in your ceiling, but really look at the density of the material you've got in there, because it's probably very, very light. And I think and as I say, if you hold it up to the light and you can see through it, it's probably not dense enough, and that's probably why it's not doing the job.
Yeah, I actually bought the one that was the so-called high density one. So when you hold it up, you can't actually see through it.
Okay, it should be more effective though. So as I said, I'd have to, maybe we'll send me photographs and must have a look, because we've said that the 100 mils of or 110 mils should be sufficient. But again, yeah, Denzel. Yeah.
Thanks, Kiran, for sharing. I just want to also maybe ask, because we look at it as a system,
Yes.
as opposed to individual, just individual materials. As a system, then we are saying that various components could lead to the effectiveness of whatever is being used.
Yes.
So in Kiran's case, is it that the entire system should be analyzed properly to actually see, is the 110 effective, or would it have always been effective, but somewhere else he's failing in the system? And that is why he's not achieving. So each case in point, you'll have to look at it individually and analyze it as its own system. And maybe it's not about it not being 110, it's just that he's losing somewhere else. Yeah.
No, that's why I said to him, I'd like to see photographs, because he's saying he's got a huge cavity space, huge void. It's maybe that there's something that is preventing this from doing its job. And that's how, and again, I love this example. And the reason I love this example is because people are hung up on thicknesses, look, I've found places where, so in the main interior of the country and in the Western Cape, it says that you need 135 mils of glass wool. And what we find is that the polyesters are saying, okay, you need 135 mils of polyester as well. Like they're saying you need 100 mils of polyester. No, it's not about thickness, it's about performance. And every material has a different performance. So you have to look at the system to see what is it giving you. That's also why I asked about windows, Because sometimes, and it's also about air leakage. When, especially, I mean, in winter is quite. It's easier to look at it in a way that, you know, I've been to a house where they said to me that the insulation wasn't making the house warmer. And while I was in the house, I was standing on tiled floors with boots and socks on. And eventually, because of the air that was coming from underneath the door, I felt like my feet were frozen to the tiles. And I just said to the homeowner, you know, go to the hardware store, get that little strip of rubber and put it, you know, seal your door properly. Did that. True as Bob, she phoned me and went, wow, that rubber seal on the door really works effectively. I'm like, now maybe it's a combination of the rubber seal and the insulation in the ceiling, you know. And that's the thing is, you know, I've had other things where people said your insulation used to work and now it doesn't. And then you go there and there's this huge tree outside their window where they used to allow all the winter sun coming in. And I said, well, you know, when you first put the insulation in, how big was this tree? And over time, it had grown so much that it just shaded the winter area, and you couldn't actually get any summer, any winter sun. And you know, so it's, you know, and I'm not saying that's your job, because sure, the last thing you want to say is now don't put trees outside, because I mean that's obviously not part of your job. But when I say you look at the system, you know, when you analyze things that are not going right, you really have to look at it holistically. It's not one thing. It's always a combination of the things. So yeah, so I definitely like to see the sort of whole system. But yeah, so thanks for that. As I say, because I love that thing that people always they want to sell thickness. And the other thing, Kieran, you asked about the thermal conductivity. So let's look at this thing. I was going to, okay, so this is the thing we looked at, the insulation guide. So that's for zones 1 to 6. This is yours. And basically you can see that the different things that you need. Now, if you look underneath, I've put this compliance conversion. So if you need to know what thickness of material is needed for your area, you say, okay, the R value needed in a sort of standard roofing situation is 2.35. So I said 2.25, it's 2.35. It's K, so its thickness is K value times 2.35 times 1,000. 1,000 just converts the meters into millimeters. Meters into millimeters. So if somebody says to you, I've got this amazing product. It's only it's 50 mils, but it's equivalent to 150 mils of something else. You say, show me your SABS test certificate with your K value. And you say, okay, and you take the K value times 2.35 times 1,000, and that will give you the required thickness of the material. So I'll touch on that again because I've got an example, and we can look at it in this afternoon's session because there'll be like a little bit of a revision, and I'll go on to that. But now the other important thing is that if somebody gives you an SABS report, it must be for the exact same material. I have seen where people give an SABS report for a material that's got a different density. So the density might be 30 kilos per cubic meter, and that's the test report, but the product they're selling you is a 10 kilograms per cubic meter. And these are the things that have to be considered. And I think when you're looking at the plans, when you examine plans, you look at the thickness of insulation, there must be proof of what the R value is. And if you have any doubt, you say to the building owner, please send me the SABS test report for this material. And it's the owner's duty and responsibility to get that from the manufacturer. And as I say, it must match. The material that's on that SABS report must match the material that they're saying is going to go into the building. Sorry, I've lost my plot there. Just see, I've got more people. I just want to check if everybody's. I just want to promote some more people to panelists, because I see some of you have joined and you're not panelists. I want you to be able to talk to me. Sorry, just bear with me for 2 seconds while I put everybody in as panelists. See Sharon there. I'm promoting you to panelists so you can talk to me. There you are. I think I've got everybody as panelists again. Cool. So now, as I spoke to you as well, you get things like isolation, bubble, cushion, and they're called radiant barriers. So they work in an R value equivalence because they don't have thickness. And as I say, if you look in the SANS 10400XA, there is a table of R value equivalence. So that now again, what's the point of me telling you about an R value equivalence? And that's another thing that you might be able to do, Kieran, is if you take a radiant barrier and you use it as a roof lining, so you take a isolation, it does improve the total system R value, especially in a hot climate. Because as I say, reflective foils, radiant barriers work well in hot climates. They don't work. You can't have them by themselves. They don't have sufficient equivalent R value. You always need a combination of them and a blanket material. So, but they work well instead of a, you can use them instead of like a waterproofing. You can put them in, and you take that equivalent R value, and then you can use that in the R value system and still make sure that you get to your 2.7. Okay. Denzel, do you have a question?
Yeah, maybe this sounds stupid, but in terms of in your roof construction, your damp-proof course, your damp-proof membranes that go in,
yes,
not accounted for as part of your making up your R value.
Not unless it's a radiant barrier, because if it's just a damp-proof course, unless it's got a specific insulation property, you can't improve it. So include it. So if you think of just say a waterproofing membrane, as I said, even in the lightweight construction in the wall, it's there. It's got no I can't speak now. Reflectivity. If you think of a damp course membrane, does it have an insulating property? So if the manufacturers of the damp proofing come along and said, oh no, it's got a thickness. So if you think maybe like a bitumen product or some kind of rubber-based product, it may have an R value, but the manufacturers of that system would have to actually then measure it and say, yes, so you've got a flat, say concrete roof, and I've got a waterproofing system on top. You'd have to know what that R value is. So the manufacturers would have to measure what that is, or the designers, the professionals, would have to sort of get hold of those numbers and say, I'm now going to add that damp-proof membrane to the R value addition, but they must have proof of what that R value is. They can't just guess what it is. So I mean, if you look at it, it's got thickness, it's got some insulated property. It may add to the performance of the roof, but again, for your benefit, you need to know what is that number. When go and have it tested, and what is that number?
Can I come in?
Yes, Kieran.
So effectively then, us as building inspectors, when you go to site, when you do a roof inspection, we normally do that before the ceiling goes on. So at which point in time the damp-proof membrane or roof plastic, if they're still using that, is on, the battening is done, and the tiles, well, they're ready to start tiling or almost finished the tiling. So at that point in time, we are not able to tell whether the house will become compliant until after the ceiling goes in, because usually they'll treat the thermal issue at ceiling level. So would it not, if in effect the conventional plastic and or damp-proof membrane that's put in place is there just to retard water from getting into the roof, wouldn't then site isolation become the next best alternative to tackle, one as a damp-proof cost and two as a first line of defense, and be more effective? So shouldn't that become the law then?
Look, we've asked in areas that, yeah, you'll see in the new 10400XA, it calls for a radiant barrier as the water barrier type thing. So in some areas, in the new 10400XA does ask for it. And it is because the thing is, in hot areas, it really does help, you know, with that heat ingress.
Okay.
But
is the new 10400 now effective?
Not yet. And because I don't think you were here yesterday, but yeah, so it's not yet. It's just gone out for public comment. There are comments that have come back, which we're dealing with. But it'll probably go out for another session of public comment. And so I'm expecting publication probably, hopefully, at the end of this year. But the reason, okay, just again, the reason why I'm saying to you, yeah, please, okay, so don't quote the new one yet. You have to still use the current one, because that's, you know, people choose to go to the deemed to satisfy route. The current 10400XA is the one that is in play. But what are we doing is we're saying, heads up, guys, this is coming. Because again, you guys need to be ahead of the curve, so that you don't have people telling you what's right and what's wrong. You know what's happening.
Okay, so effectively, how does this then apply to houses that have already been constructed? Do they have to retrofit? Can they retrofit? No.
The law works that once this new 10400XA is published, unless if you've got a project that's in the pipeline, you can still there's a 6-month window for projects that are still in the pipeline. So projects that either have been to the first phase of plans examination or have been submitted, they can still comply with current 10400XA. But anything new from the date of publication of the new 10400XA, any new submission has to then comply with the new 10400XA. It can't be retrofitted, unfortunately. You can't make any law retrospective. And the only time, but obviously if there's additions and like a retrofit thing, additions and alterations, and they submit plans on those additions, then again, they have to comply as well. I want to see. Okay, guys, we must just move on a bit. I don't want to run out of time here. So let's talk about government subsidized housing again. What does government subsidized housing say for? So I've got all your chats. I think we can deal with them when we do the afternoon session. Let's look. What does the government subsidized housing say? The requirement for ceilings and roofing are. So in their norms and standards, in their red book, they ask for ceilings and 130 mils of glass wool. So when we chatted to them, I said to them, why 130 mils glass wool? Can't we put an R value in? And they were like, no, R value is it's too difficult. And our building contractors won't understand it. But now what happens is that we have to work now in glass wool equivalent, or we get to a situation where people say, It's 130 mils of any material. And then we have problems again with this thickness versus performance story. And the 130 mils was derived by a very, very complex algorithmic method. No, I'm lying. They took the 6 climatic zones, saw what the requirements were for, they added them up and they divided by 6. And that's how they got to the 130 mils of glasswool. So the challenges are, as I said, we can't work in glasswool equivalent. It doesn't make sense. We really need them to put an R value in. But be that as it may, because we're just finding people are just saying, let's just use any 130 mils. And in some of the regions, especially in KZN, we found that if you over-insulate, it's got the opposite effect. And Kieran, that's why we have to get a balance between effectiveness of the insulation, but also that the insulation doesn't hold the heat in your house. So if there's heat coming in from the windows or whatever, it doesn't hold the heat in the house. So what we've said with the hotter climates is don't go to the 130 mils. It just doesn't really make technical sense. So again, I've done the tables of equivalence, is that for 130 mils of glasswool, you need 150 mils of polyesters. And all polyesters are not created equal either. All insulation is not created equal. All polyesters are not created equal. You get ones with very, very poor thermal conductivities. Then you're looking at like 182 mils. And again, with the extruded polystyrene, I've excluded the sealing. Okay.
Lisa,
Again, yes.
with regards to human settlements, is this going to be part of the new legislation that you're talking about?
No, unfortunately not. So I'm just telling you what's in the Department of Human Settlements Red Book, because that's what they deal with. And as I said to you yesterday, I find different municipalities approach this differently. Is that some municipalities say, if you're building in my area, you must build to some kind of standard, whereas others, the Department of Human Settlements or the NHBRC said, this is our area, we're very territorial, you don't have a say on this, which is unfortunate. But what I wanted to say is that the low-cost housing is not excluded from any sense of energy efficiency. It might just be at a different level. And so I'm just sharing with you what they have in their book. And look, ideally, understand behind the scenes, we are working hard to try and get them to comply with national building regulations.
Okay, and so, if they comply with category 1 buildings?
Yeah, and that's why there's category 1 buildings inside 10400s, because that was the Department of Trade and Industry saying, yes, we will include the concept of affordable housing inside the norms, inside the 10400XA, well, inside all the 10400 series. And that's where the category 1 buildings come from. So
why I'm saying is because on those buildings, they only call for bagwash.
No, but they don't actually. They don't call for bagwash, I promise you. They call for a plaster. It's bagwash is people's interpretation of it. If you go to the standards, you go to their norms and standards, to their red book, it asks for a plaster, not a bagwash. Okay. Somebody has interpreted it to say bagwash.
Yeah, I know. It's just a challenge for us as a municipality, because when we try to enforce, we've always been seen as we are being demanding, and most of the time the guys come through and say, you know what, we have not budgeted for it, so therefore we cannot provide it. So
that's my problem, is that it's included in the government's budget. The plaster, it's been worked out, it's been calculated. The money has, should cover plaster.
I think they're redirecting it for other uses.
Perhaps they are, but that's the point, is the plaster is budgeted. People can't say, I can't afford it. It's in the breakdown of the budget. So when, there's a letter that went out, and they showed increased money per new intervention. So there was increased money for the ceiling, there was increased money for the insulation, there's increased money for the plaster, there's increased money for the windows. So there is, the budget should cover plaster. If it doesn't, there's a problem. And as I said to you earlier, the bag wash doesn't stop mold growth. And mold growth is dangerous.
Okay,
so again, you're not hindering them, you're helping the health of the society. But thanks for that, Shane.
No, thank you.
Okay, let's move on. Okay, so these insulation types, I said, you know which was which. Top left is laminated polystyrene. It's probably XPS, EPS, expanded polystyrene. Middle picture is external insulation, a wall system. Top right, think pink aerolite. Bottom left is what we call cellulose fiber. So it's blown in recycled paper. So it's normally blown in recycled newspaper. It's got a fire retardant added to it. Then a normal glass wool blanket. It's not pink color. It's not, the real color is yellow. And then bottom right is a tongue and groove extruded polystyrene roofing system. So these are all the different types that you get. Now, as I said, remember my little triangle, and that's the, oh, everything's shifted down. I'm going to have to fix the specs. I think, when we transferred over, sorry, some of our labeling went down. So basically what it says is that you, and I showed you this in that little drawing earlier, is that if somebody says to you, I have got this wonderful new insulation, and you only need 50 mils of it, you say, okay, tell me what your thermal conductivity is. Thermal conductivity times 1,000, convert millimeters to meters, and or other way around, and your intervention R value is 2.35. What do you get? And so what I'm going to do is I'm going to send this to you. It's got the answer as well. And when we look at when we go to the afternoon session, we'll discuss this again. We'll discuss this case study. So I'm not going to touch on it. I'm not going to explain it. We'll do it this afternoon if you, and we'll go through how we calculate this. So don't stress about that. And I'll talk about this walling as well. We'll do both of those. So the next part we've got is sealing, as in S-E-A-L-L, not C-E-I-L-I-N-G. And we have to seal the buildings, because we don't want to have, as I said yesterday, we don't want to have leaky buildings. We want to have ventilation, but we don't want to have a leaky building. So it really just says you must have caulking, skirting, architraves, cornices. Minimum air infiltration in the ceiling voids. There must, if you've got a fireplace or any kind of fossil fuel burner, you have to have and you have a chimney. Your chimney or your flue has to have a damper in it, so that in the summer you close it. And to make the building inspectors' lives easier, we've also said that on doors, that you must be able to see the seals. That, you know, they can say to you, they can give you the values of the system, that it's less than 2 liters per second of air coming in, and you say, no, I want to see that there's a seal on doors. And this is in the new 10400XA, because unfortunately in the current 10400XA, we talk about sealing of fenestration, we talk about sealing of windows, we talk about sealing of glass doors, but we didn't look at the sort of solid doors. So now we're looking at solid doors in the new XA. So again, this afternoon, we will discuss heritage buildings, what to do with heritage buildings. And I know your first instinct will be don't touch them, which is normally the instinct. But as part of this afternoon session, we'll look at this case study of heritage buildings, and we'll discuss how heritage buildings can be made energy efficient. So guys, you can also think about it in the break. So let's look at services. as you've said, but hot water is the law. It's in the regulation. The regulation says that a minimum of 50% of hot water must be given by means other than electric resistive. So maximum 50% by volume of hot water can be given by electric resistive means. It's the law. So what it really says is 50%, a minimum of 50% must be provided energy efficiently. So we look at insulating the hot water cylinder and the exposed pipes. When we say exposed pipes, we look at insulating a meter of before the inlet, 1 meter of inlet water, and any pipe that provides hot water, exposed pipe that provides hot water, we must be insulated. This drawing, this picture that you can see, this photograph that you can see, it's a thermal imaging photograph. I don't know if you guys have come across a thermal imaging camera. What it does is it basically, you point it at something and it shows you the temperatures of the object that you're looking at. So the picture on the left is just a hot water cylinder without insulation, and the picture on the right is after it's got a blanket on, and you can see it's you know, these minimal areas of where are very hot. Why do you want to insulate? Because again, those hot areas are where the heat is escaping, the energy is being lost, so that you're not keeping that water hot. You're allowing it to escape into the roof void. People often ask me, they say to me, oh, well, you know, there's insulation already in the cylinders. One of the questions I'll pose to you, and we'll deal with it again in the afternoon session, is why, if there's insulation, the manufacturers put insulation in the cylinders already, why do we still have to put a blanket over? So I'll pose that to you also for this afternoon session. So types and examples of the non-electric resistance heaters are soda water pumps, heat pumps, biogas, natural gas, LPG, sustainable source timbers or invasive vegetation, and heat recovery from buildings. So if there's a big, whenever people look at this hot water ruling, this hot water regulation, generally they say, oh, well, therefore we have to put soda water heaters in, or we have to put heat pumps in. No, there are other alternatives. The thing about burning sustainable source timbers and invasive vegetation is you must just watch what you do with the emissions that come off it. You must just you must be in a space that's well ventilated, so generally it's outside. Heat recovery, an example of heat recovery is a lot of gyms, and the Virgin Active gyms, they use the exhaust heat from the air conditioning system to heat up the water. So instead of just letting that hot air go out into the atmosphere, they then take that so as the air conditioning system cools down the building, they use that hot air that comes off as the heat exchange, and they actually use that hot air to heat the water. And that's why often in gyms you'll find that they don't run out of hot water, because they're using the aircon system to heat it. So that's an example of heat recovery from an external process. It's just so that you know. And then I put in brackets there, not PV, and we can also talk about that this afternoon. So I said there was heating via PV not included, and the compliance criteria is given in 10400XA because each of these types of alternative heating have to obviously have some kind of compliance criteria. It must be given because you can supply hot water by an alternative means, and if you don't watch how you do it, it can be energy inefficient, if that makes sense. So we give compliance criteria saying that you have to do a proper calculation, and we'll also talk about why would it give a bad result. We'll have a chat about it this afternoon when we do our open session. We'll go through everything, and we will also discuss why PV is not included. But inside the standard, you'll see a table of hot water consumption, usage, and the storage. We spoke about storage yesterday. So the only time you don't insulate pipes is if they're part of the heating system. But if so, you wouldn't find it really in your area, but in Gauteng and the sort of areas where it gets colder in winter, sometimes they use the hot water pipes to heat the inside of the house. But then you have to have some mechanism where in the summer you close off that heating mechanism. But I mean, it's quite unusual, that kind of heating system. But generally, all exposed pipes should be insulated. And exposed pipes are the pipes, as it says, exposed. The pipes that go into the warning system are not exposed, and therefore they don't need to be insulated. So, and those are the R values that are needed for the different diameters of pipes. And again, we use the 60 degrees as the temperature. It's just the effect of pipe insulation. So people always say, well, it's just these little pipes, does it have an effect? Of course it does. It really makes sure that the hot water gets to where you need it to be. Here are some examples of non-electric resistance heaters. So you've got solar water heaters, domestic heat pumps, gas. I mean, you don't normally use the little bottles for your gas water heating, and it's got its own sort of requirements there. But you can use things like, there's ICLEI gas, there's gas from Moss Gas, Sasol gas. You can use those systems. There's biogas digesters. You can use different biomass, and that picture on the left is an example of heat recovery from an air conditioning system. And so you can use all of those. Solar water heaters, okay, they are only effective if orientated correctly. I don't know in your area if you've got a system where, or a whole lot of houses or cluster developments where they've got solar water heaters. We've come across housing developments where you're lucky if you can find two solar water heaters facing the same direction. Depends where the roof is, how they've put it on, and it's crazy. The effective solar water heating is only if they are facing north and being able to collect the sun's energy as much as possible. So again, we face north because of our position on the planet. So one of the things, guys, even in the drawings, we've come across a plan where they've put a solar water heating system in, and then the roof system needed a retaining wall. And what they did is they put the wall right in front of the solar water heating system, so that solar water heater never sees the sun because the wall is in front of it and it blocks it from any collection. So these are the kind of things as well. Sometimes you look at your plans, you go, oh, there you are, there's a solar water heater, tick the box, it's there. Please also look at where it is it facing the right direction, and does it have anything that potentially can shade it? Look at lighting. So in the current 10400XA and in the new 10400XA, there's tables for maximum lighting power density and demand. So basically, what it's saying to you is, as I said yesterday, occupational health and safety comes first. So the lux levels required to do your tasks are sacrosanct. You have to have the right amount of lux on your working surface that the occupational health and safety requires. What this energy efficiency standard says is you must give the right lux level, but at the lower energy. So if you look at it, incandescent light bulbs. We used to have, they used to be 60 watts, 100 watts. Now you've got the CFLs, compact fluorescent lighting. The LEDs is slightly emitting diodes. And they give the same lighting level at much lower wattage. So the CFLs are generally 10 to 11 watts as opposed to 60 watt light bulb. And that obviously is just lower energy. So we're saying the right kind of lighting must be there, but just do it at a low power or low energy requirement. In the new 10400XA, what it says is that in housing, if you've got LEDs or CFLs, you're deemed to satisfy. So then you don't have to do a lighting power density table or demonstrate a compliance to lighting density. And what the new 10400 also says is that in areas not housing, so in offices, shops, all other occupancies, where there are unoccupied areas, you must put a motion sensor in. So a motion sensor, I think you all come across them. As you walk and the motion sensor senses you, it turns the light on. And this would be in corridors, in meeting rooms, in bathrooms, in places where people don't sit all the time, but when they're in there, the light must go on. And so in the new 10400XA, it asks for, it mandates that motion sensors must be put into unoccupied areas. So this is the lighting technology. So the question is, which of these lights are least efficient? And I like to always make the comment here is, what did South Africa have before candles? We had electricity. So, little joke. But the most efficient light bulbs are obviously the CFLs and the LEDs. The incandescent light bulb is inefficient. The candle's efficient, but it doesn't have the right light level. So you can't use a candle because it doesn't have this, the legal light level that you need. Again, we look at efficient services, HVAC systems, lifts. Again, there should be energy labels on it. It's you know, any calculation that goes with it, it must be given by the manufacturer. Appliances, as I said before, they're not included in the design. Server rooms are not included in the 10400XA design or the National Building Regulation XA design. They are covered by, and there will be more and more appliances will be covered by energy labels. At the moment, it's just fridges and washing machines that are, it's fridges and washing machines that are mandatory. But you'll see more and more appliances, different standards, they will have appliance labeling. Does not fall under the building regulations at all. It's got totally different standards. You don't have to worry about them. Yeah? Shane?
I just want to ask, in terms of, hi, in terms of, we're saying light bulbs, and from a building inspector's perspective, when we're doing a completion inspections and so forth, and the light bulbs are not fitted as per what the approval will be granted in terms of either LEDs or and the like, that's going to become a little bit of a challenge.
Yeah, no, look, I understand that, and that's the problem. Like, you know, you were even saying, like, you know, you do the roof inspection before the ceiling's there, but you can do final inspection and just have a, you know, pop your head through the roof, or take your like little periscope thing and look up. But again, we're saying, okay, let them be on the drawing, and there's discussions that to make incandescent light bulbs actually illegal. They're slowly being put out that they're not going to be an option, but that's still in the process. So it is a problem. So what we're saying, okay, first prize is let's just get them to put them on the drawings. That, you know, that there is going to be CFLs, there is going to be LEDs, or they have to show you the light density calculations on the drawings to say this is a lighting type that's going to be put in there. But I agree with you that unfortunately, I mean, not everything can be inspected, but where possible, obviously, just, you know, look for it. But as I say, the move lighting's probably the easiest win that we've had. Is there's very few incandescent light bulbs, probably in the low income areas still, but generally most light bulbs will be are LEDs and CFLs, because people understand that they do really cut down on your energy bill a lot. It's the easiest win. But I agree, it's not, you know, and unless you say to somebody, I'm going to do a specific lighting inspection, understand that it's you know, what's on the drawing may not be what's put into the house or into the building, and unfortunately it is difficult to say I'm going to inspect to 100% inspection. But again, you could always say to people, you know, let's inspect, and I want to see, you know, even your store of light bulbs that you're going to put in something. But you know, I understand that it's problematic. But if you can, obviously that's first prize. Okay, I just wanted to show you as well, you know, we spoke about costs and things like that. I was watching the time, we're almost finished. And there was, in the Western Cape, Belhar, they actually built, it's a social housing thing, and they built a 2-edge rating tool, which is a green rating tool. And I just wanted to show you the effect of making buildings green. So as I say, it's a social housing development where they watched money like crazy. It was funded, Nedbank helped the funding, and this was the saving that they got. In the 2-bedroom houses, they saved 42% of energy. They worked out that the utility bill, the yearly utility bill was worth 1 month's rent. So basically, by having an energy efficient and a water efficient building, they saved a month's rent in utility. So they basically were able to, you know, that they didn't, because they didn't have to pay that extra money, they actually managed to pay 12 months worth of rent. And effectively, as I say, they saved a month's worth of rent. So I just put this in just to use that as an example, because we spoke about payback of materials, payback of these energy efficiency interventions. And I just wanted to show you how possible it is, and the knock-on effect in real numbers. So as I say, I just threw that in as a bit of a thing. We can discuss it later this afternoon if we need to, but we did discuss it a lot yesterday. So if we look at it, owner is always responsible. I know they always say competent person, and we spoke about this yesterday. The architect must do their due diligence. They've got professional indemnity and they should look after it, because they will be liable if things go wrong, and the owner, the buck stops with the owner. And again, what the Consumer Protection Act says, that if a standard exists, it will be expected that the material provided satisfies the standard. So again, there's other things that also protect the consumer, and even with services, the architect has to tell them to the best of their ability what is needed. So what I would like you to also think about is, for this afternoon session, is, you know, what are your challenges? You know, we've touched on some of them, and it's really what would you like to see in the next versions of 10400. So don't worry about the plans, I'll take that out. We're not going to do the plans. What would you like to see in the next versions of 10400XA? You know, we've tried to make it more user-friendly. Have we succeeded? Like, we've got rid of the fenestration calculations. Are you rejoicing? Are you not? And if we do a water, well, not if, when we do a water efficiency standard, is there something in particular that you'd like to see? And I know that we've got quite a few water guys in the audience, so please also give it some thought. So as I say, again, I'm going to put this together, and we're going to send it to you in the break. And then when we start, we'll start at 1 again, and we'll do our open session again, and we'll discuss some of the questions that I've asked, the case studies, and we can also touch on where we're going to and what your challenges are with 10400XA. So please give it a thought, and this will also be part of the presentations. So you'll see all our contact details. And as I said to you, I offered to say, if you have questions, if something happens and you want to contact me, there are all the details that you need. So please contact. So with that, our session has come to an end. I think we're just slightly over, but not a problem. So I hope, I'm going to sign off, and I hope I see you all at 1 o'clock. Please have, and as I say, in the interim, we'll send you the rest of the presentation. And yeah, eat, drink, be merry, but be prepared for our next session. And let's hope it's as interactive as yesterday's session. I really enjoyed yesterday's session. So guys, with that, I'm going to sign off. And, oh, and there's a thank you from, let me go back again, sorry. Thank you again to the Building Efficiency Accelerator people for making this possible, and for facilitating this, these training sessions. Much appreciated. Okay, guys, I will see you this afternoon. So, let me just find where to stop. Stop share. Okay. And bye to all of you.
Bye, Lisa.
Bye, Sharon. Thanks. See you this afternoon.
Okay.